Well, hello everyone. I'm Paul Gribben and I'm an Associate Professor of Marine Ecology at the University of New South Wales. I'm also Director of the Sydney Harbour Research Program, and it's my pleasure today to introduce this fourth edition of the World Harbour Program webinar series. We've got a range of wonderful speakers today. I'll be up first. Following me will be David Aguirre from Massey University in Auckland, and he'll be talking about current and ongoing research focused in and around northeastern New Zealand, with a particular emphasis around the Auckland region. Following that, we'll have Cartiona Macleod and Christine from UTAS and the Derwent Estuary Program, respectively. Cartiona is part of the Fisheries and Aquaculture Group, and Christine is part of, as I said, the Derwent Estuary Program, which is a multi-stakeholder vested group interested in issues around sustainability and those sorts of things in the Derwent Estuary. But to start today, the other thing is David will not be online. We won't be able to see him. His video is not great, but he will be presenting a wonderful seminar and you will be able to ask him questions. So what you'll see in front of you today, hopefully, is probably a picture of one of the most beautiful and stunning harbours in the world. I'm sure you would all agree. To get you orientated, part of the talk is centred around this idea that Sydney Harbour is kind of divided into two halves. We've got the east of the harbour bridge, which extends to the left of your screen, and the west of the harbour bridge, which extends to the right of your screen. So that's just to get orientated. East of the bridge goes towards the harbour entrance, and that becomes a little bit more important later on. So some physical aspects of Sydney Harbour. It's a drowned river valley, and it has a diverse physical environment. I see on my screen some of my words have been cut off. I hope that's not going to happen all through the seminar. So this drowned river valley creates dramatic variation in depth and light throughout the harbour. We go from essentially intertidal areas to areas that have greater than 50 metres of water depth, so we can have some very diverse communities again, which I'll touch on a little bit later. Because it's a drowned river valley, we have highly variable flow rates throughout the harbour. Now this particular slide only shows to the west of the harbour bridge, which is going up the Parramatta away from the entrance. So the harbour bridge would be just on the right-hand side of your screen, where the water flow starts. So we're getting water flows anywhere from sort of above 0.51 per metre squared, depending on freshwater inputs, down to some fairly stagnant waters. And this creates some areas of that differ greatly in their turbidity and in their sediment grain size. So apart from the physical, some of the really diverse physical attributes of the harbour itself, somewhat surprisingly, has an incredibly diverse fish fauna. Now, Sydney Harbour has almost 600 recorded species of fish. And that's predicted to grow given the tropicalisation of the Sydney area and the vagrants that are coming down from tropical areas. And you can see that Sydney Harbour itself has more fish species than the entire coastline of Great Britain, New Zealand, Sweden, and San Francisco Bay. But the other side of diversity in Sydney Harbour is the invertebrate diversity. Now, in total, molluscs outnumber the fish species 2 to 1. We have incredibly diverse crustacean fauna, polychaetes, and also echinoderms. Now, it's likely that although we've got sort of more than 3,500 species recorded, that we're going to have many, many more species in this, because these are just often just one-off recordings from the Australian Museum. There's actually been very few targeted taxonomic studies of biodiversity in the harbour. So what supports this really high biodiversity? Well, because Sydney Harbour is a drowned river valley, it has a really, really high diversity of habitats, which supports this local biodiversity. So we have a range of intertidal rocky shores, subtidal reefs, and a whole bunch of sandy bottoms, from very fine, low-flow systems to very coarse, beachy type sediments. Now, in a recent review by Pat Hutchings from the Australian Museum, they suggest that there's potentially more than 3,000 species living within our sandy bottoms within the harbour. Now, I guess one of the hardest sells in terms of convincing people of importance of habitats are sandy bottoms, but in most estuaries, I think we'd all agree that the most important habitat in terms of how systems function are the sandy bottoms, and it's certainly the most dominant and omnipresent habitat in Sydney Harbour. So west of the bridge, as we go away from the harbour entrance, we also have a diverse macrophyte fauna. So we have a range of mangroves, we have some salt marsh communities. These are actually listed as an endangered ecological community in New South Wales. We also have 3 or 4 different species of seagrass. Now, the one in the middle there, Posidonia australis, is again listed as an endangered species in New South Wales. And most of the seagrass, not surprisingly, occurs just inside the harbour entrance, so not to the west of the harbour bridge. We also know that over time we've lost a large extent of these really important habitats that support our high biodiversity. So since we started recording seagrass beds in around the mid-1940s, we've lost about half of the seagrass beds within the harbour. We've lost sort of probably 90% of the salt marsh within the harbour, but perhaps not surprisingly, the mangroves haven't changed a lot at all, given that they tend to like sedimentation and can do reasonably well in urbanised sediment environments. Now, Sydney itself, or the Sydney Harbour, is managed under the Marine Estate Management Authority by the New South Wales Government. And Sydney Harbour itself falls under this Hawkesbury Shelf bioregion. Now, this is a bioregion that extends probably some 300 kilometres from Newcastle in the north to Wollongong in the south. And Sydney Harbour, if you use my cursor is just in here somewhere. So it forms part of the Hawkesbury Shelf bioregion. Now, one of the main goals of the Marine Estate Management Authority in New South Wales, one of its major visions, is to have a healthy coast and sea managed for the greatest well-being of the community now and into the future. So some of the threats and challenges to the Hawkesbury Shelf region and to Sydney Harbour itself have been drawn up in the schematic that was lifted from the MEMA, or Marine Estate Management Authority, one of their recent reports. And they're very similar to most of the other challenges that we see in many of the other harbours, or most of the other harbours around the world. So we have problems with shipping. We have one in New South Wales which is to do with estuary opening, and that many of our estuaries are actually icoles, which are intermittently opened and closed estuaries, so they actually close naturally themselves. That doesn't occur in Sydney Harbour, obviously. The two that I've highlighted in yellow that we've focused a lot of our research on in Sydney Harbour, urban stormwater discharge issues around that, and foreshore development. And these are two components that I'm going to address in a little moment regarding some of the research that's been going on in Sydney Harbour. So I'd like to come back to this idea that Sydney Harbour is a harbour of two parts. So to the east we have the Easterly Harbour Bridge, which in this case is the arrow going north. It empties into the out the open ocean. So in this part of the harbour, most of the harbour is actually in pretty good condition, and we know that water quality has greatly improved in this part of the harbour, and there's very, very high biodiversity. So as part of the Sydney Harbour Research Program, part of our ongoing research in this area is not just to bring back ecosystem function, but ask questions about, can we fully rehabilitate this part of the harbour so that we can completely enhance all user experiences. Can we bring back fish stocks? Sydney Harbour is highly utilised by recreational and commercial fishers. There's a very strong link between fish recruitment in the harbour and commercial fisheries outside the harbour. So we're starting to look at whether we can enhance fish stocks through habitat rehabilitation. But we also know that in many of these areas, particularly some of these bays up around the very eastern side of the harbour, even where water quality is reasonably good, some of the ecosystem function hasn't come back. So we're currently running some experiments to see whether we can kickstart some of the ecosystem function in these areas using macro interactions. And is that can we use bivalves and other bioturbators to stimulate and restore some of the ecosystem function in these habitats? Now, west of the Harbour Bridge, it's a different story. We have a lot of historical pollutants and other pollutants that are continually coming into the system. So some of the questions that we're asking in this part of the harbour are, can we actually enhance any ecosystem function? Can we bring back any biodiversity? Can we get the sediments to function in any way that helps promote a healthier ecosystem? And a lot of this research in this part of the harbour has focused around stormwater. And we can see from the two graphs here, we've got on the bottom right-hand side, we have the flow rate graph that I showed you earlier, and we have on the top graph, we have the levels of lead in sediments and fine fractions in sediments as we go up the harbour. And there's certainly, if you compare these two graphs, there's certainly a very strong link between water flow and heavy metal deposition within the sediments. And especially as we get to the western side of the harbour, so the harbour bridge is down here. As we move to the west of the harbour and flushing rates are low, we get lots of these more stagnant areas, and there's lots of stormwater input. We tend to get a lot of build-up of pollutants in these areas compared to the eastern side of the harbour, which is more flushed and much more healthy. Now, even though the water quality in Sydney Harbour has improved greatly, almost 2/3 of all pollutants enter via stormwater drains, and some of these hotspots pollution have pollutants that are 20 times higher than natural levels. And approximately 3,000 tonnes of sediments, pollution and nutrients are dumped into Sydney Harbour every year. So it's a lot of residual and a lot of ongoing stormwater into this harbour. So some of the research that's been done, part of the World Harbour Program, the Sydney Harbour Program, the Sydney Harbour Research Program, has been looking at some of the scales of variation in stormwater and patterns in stormwater deposition and pollutant deposition around stormwater drains. Now, a lot of this work has been conducted by Katie DeFawn and Emma Johnson's group in conjunction with a bunch of government and other university agencies that have vested interest in Sydney Harbour. So this particular study that I'm going to show you looks at some of the spatial scale of deposition of pollutants in our system. And this is a particular study that was conducted over 4 months. So we had 4 locations in Sydney Harbour. We looked at patterns of ecosystem function and deposition at 2 different sites. We had, 2 different locations. We had 2 channel sites, 2 channels, 2 embayments. So these differ in their water flows. We had 3 different sites. So we had 0, which is right next to stormwater drains, 200 metres away from stormwater drains, and 1,000 metres away from stormwater drains. And we took 4 grabs and cores at each site. So when we collected these grabs, we measured a whole range of different metal contaminants, chlorophyll A, silt content, microplastics. We looked at infauna, including microstructure, microfunction, and viruses, and we looked at aspects of productivity. So we know, and it's probably not surprising, that channels and bays differed in their sediment chemistry. If we look at the bottom axis as we move from left to right, we see that the 2 embayment locations are generally scattered to the right-hand side, and the 2 channel locations are scattered to the left-hand side. So the embayment locations had higher salinities. They tended to have increases in total organic carbon, total nitrogen loads, and higher lead, zinc, and copper. Within this graph, we can't really see a lot of the patterns around distances away from the stormwater drains themselves, but it appears that actually most of the deposition is happening around 2 metres away from the stormwater drains themselves. So the channels and bays also differed greatly in their bacterial communities, and again, as we go from left to right on the bottom axis, we have the higher flow sites on the left-hand side and the lower flow sites on the right-hand side. And to summarise these different bacterial communities, towards the right-hand side, we have communities that are generally associated with more anaerobic or low oxygen environments, compared to the left-hand side, where we have more coarse sediments and bacteria more aligned with sediments that have higher oxygen levels and more healthy sediments. We were also able to extract some of the virus communities from the stormwater and reference sites, and we just have some little micrographs of some of the virus stands and a slight green stain of virus-like particles. Now this graph doesn't show you the types of viruses that are there, but it does show you that the stormwater sites and the reference sites clearly have very different virus communities, or viral communities. So the other aspect that we've been doing a lot of work on, and most of you as part of the Derwent Harbour Program will be very familiar with some of the research that I'm going to show you now, is this idea of this aspect of harbours and continuing urbanisation and the conversion of natural substrata to artificial structures. Now, in terms of Sydney Harbour, more than 77 kilometres of the 332 kilometres of coastline of the harbour have been replaced by either hard substrata, pilings or rock walls. So more than 15% of the coastline has been replaced with seawalls. We have more than 40 marinas and more than 35,000 recreational craft. Now, we all know that Sydney's population is meant to grow from 4 or 5 million to around 8 million in the next 10 or so years. So potentially the harbour use is going to double, and the pressures to increase urbanisation and for increased growth in the harbour are only going to increase. So one of the things we know about urbanisation, or the transformation of natural substrata to hard substrata, is that they replace rocky shores with seawalls that provide smooth and homogeneous structures, and they often don't replicate, or mostly they don't replicate, the structures of rocky shores. So this will be an experiment that most of you are familiar with, and this is an experiment where addressing whether if we could alter the complexity of the surfaces of these urban structures, can we bring back some of the biodiversity to these structures and actually increase the survival of many of the native species that should be found in these environments. So the experiment that was conducted was we put flat plates, flat concrete plates, plates that had 2.5 centimetre ridges, and plates that had 5 centimetre ridges on rock walls. And the response of these was to look at whether the differences in surface or complexity increased oyster survival and potentially ecosystem function by enhancing water filtration, and whether they also increased biodiversity. So after 1 month, there was lower predation, fewer cracked oysters on the complex plates compared to the flat plates, and we also had much higher recruitment of oysters and recruitment of sessile and mobile invertebrates into crevices. So it looks like by adding some simple structural changes to some of these urbanised structures, we might actually be able to bring back some of the ecosystem function back to these urbanised areas, and that's going to benefit everyone. So that's just a potted history of Sydney Harbour's physical and biological environment, and some of the ongoing research that's been developed within the World Harbour Program, and the Sydney Harbour Research Program. Thank you.
Working. Is it showing our screen? Maybe it is. Is that showing our screen, everybody?
Yes, I can see it.
Oh, sorry.
Okay.
I'm just, hello, everybody. It's Katrina and Christine here. We'll start, Christine's going to start off with the overview, and then I'm going to touch on the research.
Yeah, good morning, everyone, and thanks very much for the World Harbour Program team for putting this on. I'll start with a brief introduction to the Derwent Estuary, where Hobart is located, a bit of the setting and the key issues for the Derwent, and then Katrina will give us a bit of a whirlwind tour of some of the current research and recent research going on. If we have a little time, I'll just say a few words about the management program, but there's some additional slides at the end of the talk for those that are interested. So,
sorry, people. Oh, just that's not loaded as a slide. There you go.
Great. All right.
Just up and down.
Up and down. Okay. So the Derwent is located in southwestern Tasmania, which is directly south of the big island of Australia, and the capital of Tasmania is in Hobart, which is located just here. The estuary itself starts up in the World Heritage Areas of Tasmania. Lake St. Clair travels up over 100 kilometers downstream to the head of tide at New Norfolk. And then we've got about a 200 square kilometer estuary. Again, with Hobart located on the western shore. We've got a population of about 200,000 people living around the Derwent, which is about 40% of Tasmania's population. It's a fantastic estuary. I think we probably give Sydney a run for their money in terms of scenery, ranging from beautiful riverine landscapes up at New Norfolk, intertidal areas, large sandy bays, and as well as rocky coastlines and temperate reef communities. So very wide range of habitats and species. Very heavily used as well, long history of urban and industrial development, as well as recreational tourism, and a major center for Australian both marine and Antarctic research. The setting itself, also we have a classic drowned river valley system here, although this is very much of a salt wedge estuary. We have a very large river at the head of the estuary, about 100 cubic meters per second. And it's a very highly stratified system. As you can see, freshwater overlying saltwater. It's microtidal, so we have a relatively small tidal range. Rapidly flushed, about a 12-day period from the time water comes in at the top of the estuary to the time it enters at the estuary mouth. We also have very strong seasonal patterns, both with respect to rainfall and river flow, but also with respect to nutrients from the Southern Ocean versus the East Australian current. The catchment above the estuary is quite large, about 9,000 square kilometers, and until recently it's been quite undeveloped. That is starting to change, however. However, it is heavily modified for hydropower, so we have 10 major dams and over 20 man-made storages. Hobart's water supply has taken the most majority of it from the Derwent just above the head of tide, as is water supply for a large paper mill located in that area. The catchment water quality historically has been quite good, but again, we're starting to see that change with further development up the catchment. As mentioned, we have one of Australia's largest and oldest paper mills established up at the head of the estuary. That was in the 1930s, and one of the world's largest and oldest zinc smelters at Risdon, which was established in 1917. Neither of those industries had much in the way of wastewater treatment until the 1970s or 80s when environmental regulation came on board. We have also 10 sewage treatment plants currently treated to secondary or tertiary level. We have hundreds of large diameter stormwater pipes which discharge whenever it rains. As mentioned, a number of sources up the catchment which are increasing, including intensifying agriculture, grazing, cropping, dairy, as well as forestry and some very large fish hatcheries. At the same time, we have quite a lot of marine aquaculture, particularly salmon aquaculture in the nearby D'Entrecasteaux Channel, as well as now starting to develop in Storm Bay off the estuary's mouth as well. So, as a result of those combined urban and industrial catchment and other sources, we do have a legacy of environmental issues, which are both historic and current. Probably the most dramatic of those is extreme heavy metal contamination of our sediments and some of our seafood by mercury, lead, cadmium, zinc, copper, and arsenic. We're seeing some early signs of system eutrophication in the upper estuary, particularly around algal overgrowth of some of our seagrass beds. We've seen historically a loss of biodiversity, filling of wetlands, those sorts of things, as well as very large numbers of exotic species which have invaded the Derwent, particularly from the northern hemisphere, Mediterranean and New Zealand. And starting to see some multiple use conflicts between industrial development, urban development, primary industries, as well as overlain with climate change. So I'll hand on here to
Thanks, Christine. That's a great introduction. So I'm going to talk a little bit about the history of research in the Derwent. And as Christine said, there's a long history of industrialization in the system, and so the research really kicked off in the early 70s. First off with a SARO study where there was initially some shellfish culture, and we had some issues of seafood safety, and people got sick basically from eating the oysters, and that kicked off a SARO study which showed quite high levels of some metals, particularly zinc, in those oysters. And then prompted some research by Harry Bloom, Professor Harry Bloom, and he really was an environmental champion for the particular metal issues in the Derwent. His career probably suffered fairly intensively in early years because of that. He was not viewed, held up as a hero. He was definitely a bit vilified in the first instance, but he set the ball rolling, and thank goodness he did. He did some amazing early work. So from that, I'm going to talk now about some of the more recent research. There's been a lot of research in terms of the heavy metal contaminants, particularly in the Derwent, because that's probably one of our biggest issues. And whilst we talked earlier, we probably have very similar issues to many of the other harbours as part of the World Harbour Programme. I'd suggest in terms of heavy metals, we probably really do lay everyone a bit dead on some of that. We've got some very significant heavy metals. From a scientific point of view, this is an awesome estuary to work in. But there's also issues, as Christine said, with eutrophication, which may be coming more so. Habitat degradation, introduced species is a big one, and I'll talk right at the end about some particular issues in that. And as a result, the interactive effects of all of those, as well as the industrialization and urbanization on biodiversity. So in terms of the metals of interest, here's where I can show you just how special the Derwent is. Key metals that we have would be zinc, as a result of long legacy inputs from the zinc smelter. ANZAC, Australia and New Zealand guidelines for sediment levels of that are between 200 and 400 on the low to high scale. In the maximum areas, we leave that for dead around the 14,000. Mercury, as many people will know, 0.15 to 1 is the ANZAC guidelines around low and high, considered low and high levels in sediments. And in some of the bigger, more contaminated areas, we have up around 4850, which is pretty significant. And this just shows it in the context of perhaps some of those other estuaries we think of worldwide, and some which are tied into the World Harbour Project, which we may think of as being particularly contaminated. This is the mercury one. And I have to be really careful with this because a lot of people take it as being alarmist, and it's great from a science point of view because it shows just the big issue we have to deal with here and how unique the Derwent is as a test case for a worldwide scenario. But we are actually getting better, and we are actually, in many other ways, there's some very good quality in the Derwent. But I think this shows quite clearly where we sit relative to some other potentially what people might consider degraded estuaries. So in terms of what research we've done, I'm at the university at the Institute for Marine and Antarctic Studies, and we've had a number of student projects. I'm only going to focus on the last 5 years. So we had some, Jo Banks finished her PhD, and many of you will know Jo because she worked with the World Harbour Project for a time, and she worked in the Derwent looking at the biogeochemistry and showed just the effect that the bottom water oxygen levels have on metal lability within those sediments and what that might mean for biota, both the macro and micro. Really showed that low DO can lead to quite rapid release from the sediments into the pore water, and clearly the biological and ecological implications of that were quite significant. We've had an honours student in that time looking at marine fouling, who looked at differences in the fouling communities depending on the region that they're in, and showed quite big differences in the different types of fouling depending on where they were located, not just in the composition of that, but in the metal uptake. And clearly that has flow-on issues for the trophic interactions, but also for how you clear that fouling and what you do with it. Currently, a lot of it may just go straight to the bottom, and that could be further confounding our contamination issues. That work's all published, and I won't go into that, but there's some really interesting papers around that. Then in 2014, we had another PhD, perhaps more in the seafood safety. Hugh Jones looked at bioaccumulation of metal in flathead, a very intensively recreationally fished, it's probably the most popular recreationally fished species in Australia, but certainly in Tasmania and the Derwent. And there was real concern that people were fishing for this, and that represented a seafood safety risk. We found that in the flathead, yes, compared to reference conditions areas outside the harbour, there was elevated mercury. And Hugh's study picked up some previous data and said, really, we're not actually showing any sign of major improvement in those fish species, which is worrying because there's a lot of improvement in the environmental management strategies, but we're not seeing it translate into the fish. One area that we were really concerned about was, Christine talked about Ralph's Bay. It's a very lovely shallow water bay to one side of the eastern shore of the Derwent, again intensively used by recreational fishermen. And we found that there was potentially higher levels of mercury there. That turned out to be false. It was actually very consistent with the rest of it, but the levels appear elevated because the fish grow faster and they seem to accumulate it faster. But one of the other things that really stood out in there was, be careful what you wish for, because we actually found out that the higher levels in Ralph's Bay were not actually higher. The issue was that in some of the more contaminated regions, the mercury loading was lower than it might be expected, because those regions were also contaminated with selenium. And selenium was actually offsetting the toxicity effects of the mercury. So it was preferentially binding to it in the sediments, but also in the fish themselves, it was ameliorating the impacts of the mercury. So I don't know if it's a good thing or not, but going to Near Star and saying, we really don't like your mercury, but it's good that you're putting all that selenium in there. I'm being facetious, but it certainly highlights the complexity of the contamination issues in this system. Again, several publications there, and if you can access the thing later, you're welcome to look those up. Following on from Hugh's work, one of the PhD student who's still underway actually, Ding Fu, and she was looking more at, well, if the flathead have got the mercury in them, Hugh's one focused more on the flesh, but she was saying, how does it actually affect the fish itself? These levels of mercury and looking at molecular levels in the endocrine system and histology of the fish to see if it's actually compromising the fish in any way, and that work's still underway. Most recently, and Daniela has just submitted her PhD, we were looking at macrophytes as bioindicators and bioremediation tools. It's all very well to know that it's out there in the system, but what can we do about it? So Daniela was looking first at, can we use the algae, the macrophytes, to tell us a bit more about the changes in condition in the system? And she looked at seagrasses and algae, and in the end found that, so what we've got down here shows from the upper estuary through the middle estuary to the lower estuary, the levels, in this case, copper, zinc, and lead. And you can see that quite clearly in the upper estuary, much higher levels of particularly the zinc, and it declines as you go down the estuary. And that's, again, a function of where the inputs are and the dynamic nature of the estuary and the dilution. So she found that seagrass actually were incredibly good indicators of some of these metals, but they were very localized in their distribution and restricted to really the upper reaches of this estuary. But the ulva was one that was ubiquitous throughout. was an annual and had some really good potential to be used as both an indicator and a bioremediation tool. One of the interesting things about the seagrass analysis that might be useful in the biological, ecological sense is that we found that the leaves and the roots had actually, in some situations, a little bit of a different loading. So that has implications for how those plants are used within the system and also which section you take when you're monitoring. So I won't go into that in any more detail, but Daniela's PhD is available on the, will be shortly available on the website for anyone to access. Most recently, in the last 12 months, Mona have engaged with us as part of a project to look at creative thinking around solving the problems of pollution in the Derwent. And they are trying to link art students and science students with a view to getting people to think a bit more laterally and also promoting the issues so people better understanding in the community and getting scientists to think a little bit more differently, about it. And on that basis, we actually had 4 students tied through Mona scholarships last year. One was Ada Krantok, who did an honours looking at how we use oysters for monitoring. We already do that, but she refined that to look at the minimum deployment time and the size that you could put out to optimise that oyster monitoring programme. We had another student, Trong Vu Van, who looked at how we bring in remote sensing data, and this was particularly where we could use it for risk assessment. We had an oyster mortality outbreak last year, and Trung used that as a test case to say, can we use remote sensing data to better target monitoring? That was a test case scenario around a particular epidemiological event, but equally the proof of concept could be applied to other risk assessment processes. Kate Legg looked at epiphytes for monitoring and whether we could use them to pick up metals. And the proof of concept in Kate's one worked really well too. We showed a strong gradient in metal levels with plates seeded with particular epiphytes. And there's a methodology developed out of that she is part of her thesis, and again, can be picked up on our website. And Maddie Riley was looking at metal levels in little penguins. Maddie's not finished yet, but again, it was looking at that spatial gradient and whether what the penguins eat influence their metal uptake. So it's a trophic study. There's quite a few studies have been looking at habitat-focused research, focusing on salt marsh and wetlands, macrophytes and seagrasses, so that's distribution, but also how that relates to pollution levels. Barrett et al. As part of a reef life survey, we've got a really good baseline data set around some of the rocky reefs in the system. And then more recently, we looked at the effects of eutrophication and particularly aquaculture nutrients on macroalgal reef structure. As Christine pointed out, intensive aquaculture, although not within the Derwent itself, is in the adjacent water bodies and has potential to have an effect. So that is an area we're looking at, and also in the catchment in the fish hatchery areas. I'm going to finish up in the research sense talking a little bit about the bioengineering project, and we talked a little bit about that earlier. Paul mentioned it. This is our component tied into the bigger, broader picture international project. We've got 2 sites in Hobart comparing the structural preferences and the biodiversity effects. I think you've seen these ones earlier from Sydney. This is our tiles in Hobart. Interestingly, the exposed mussels, when we put them out in here, the mussels in the exposed areas detached really quickly and cleared off. They didn't like being on the outside. The ones in the crevices remained. I don't know how you managed in Sydney, but we've got some really strong little mussels in Hobart. We found actually even trying to attach them, the little critters were crawling off with the glue still on them. So anybody has got suggestions on that, it took quite a bit to get them in there, but once they're in the crevices, they definitely preferred them. This kicked off in December last year, so we've only really got 2 months worth of data, but so far, as you can see, this was photos taken only a few weeks back, so we're on the end of the 2nd month of data. Really early days, but good recruitment. Barnacles, limpets, chitons, and very clearly green filamentous algae. Interestingly for us, these are incredibly popular with the little New Zealand half crab, which is an introduced species to us. So one of the things we are a little concerned about, given our number of introduced species, is yep, we're increasing the biodiversity or the complexity with these tiles, but it might not be what we wish for. It might be all these introduced species. Hopefully that's just one stage in the successional pattern, and that later on we'll get a climax community that's got a much more comprehensive, natural, diverse community. I won't touch in any detail on other research. There's a whole list of it there. One of the things that we are very conscious of in this research that I've listed is the connection between the Derwent and the broader water body. And so a lot of this is around multiple use management and how the external influences, things like the aquaculture, could potentially impact on the Derwent. So with that, I know we're tight for time, so I will pass on to Christine to cover off a bit more on the management.
I'll just say a little bit more about management in that we do have an excellent partnership between the state government, 6 councils, and 5 industry and business partners to restore and promote the Derwent Estuary. And that's very much based on science-based management and research. We worked through a strategic plan and a partnership agreement, and the program was awarded Australia's National Root Prize in 2010 for those partnerships in good science and on-ground works. Just a bit about what we do around strategic planning, monitoring the science and investigations, on-ground works to reduce pollution, and actions around conservation of habitats and species. I'll just mention, if you're more interested in more about the program, we do have a website and regular report cards and 5 yearly State of the Derwent reports. So have a look on our website and you can find out more about it. There's a few other slides. Feel free to have a look at them and contact us if you're interested. But thank you for your attention.
Okay. So we should have my screen up now. So my name's David Aguirre, and I'm off-site at the moment, which is unfortunate as I aren't able to carry the camera as well as all the other equipment with the bandwidth that I'm on. So I'm going to talk about Auckland's harbours today, and there's a lot of commonalities with the 2 presentations that went ahead of me. But I guess first and foremost, I want to point out that Auckland is the best harbour in the world, as opposed to what Paul and Katrina were trying to convince you about Sydney and Hobart, and I can provide some data. So Auckland has the highest density of boat ownership anywhere in the world. Now that doesn't come about if it's not the best harbour. So moving right along, continuing the Southwestern Pacific theme, we've talked about Sydney and Hobart. Auckland Harbour is in the northern part of the North Island of New Zealand. And what you can see about the geography of Auckland is that it's quite different to what you might expect, given the 2 presentations that have come before. The city of Auckland sits in this narrow isthmus of land between 2 harbours, and the harbour to the north of Auckland City, the Waitemata Harbour, is connected to this fairly large sheltered embayment. And while most of the research that's gone on has actually happened within the Waitemata Harbour, as well as the regions that connect to it, which divide themselves fairly conveniently, but also ecologically into 3 different zones. So there's the Firth of Thames, which is the innermost area that's heavily influenced by a large agricultural district, heavily influenced by freshwater inputs. We've got the outer Hauraki Gulf, which is largely oceanic conditions despite the limited fetch. The inner Hauraki Gulf, which is the area that connects to the Waitemata Harbour, and the Waitemata Harbour itself. The Waitemata Harbour, again, is a drowned river valley, much like the 2 that went before us, but unlike Sydney and Hobart, we've got very limited freshwater input. The salinity of the harbour changes very little from high to low tide, even during heavy rainfall events. So in a way, it's a fairly constantly marine environment within the harbour itself. Rather than going through all of the threats and potential pressures on the Waitemata Harbour, I'm sure everyone read the reviews that we wrote in the Regional Studies of Marine Science article. I'm going to talk a little bit more about ongoing research projects and where I hope that the connections that have been developed within the World Harbour Project will be able to lead us in the future in the context of what's going on in my little part of the world. So if we zoom out a little bit and we take the Waitemata Harbour as our point of reference, there's actually another 3 harbours within 200 kilometres of the Waitemata Harbour itself. We have 2 harbours on the western side, the Kaipara Harbour and the Manukau Harbour. The Kaipara Harbour is actually one of the largest harbours in the southern hemisphere based on the surface area of the harbour itself. And both of the Kaipara and the Manukau, they empty out into the Tasman Sea. So if you were to go west from these places, you would run into some part of Australia, somewhere near Sydney. On the eastern side, in the northeast here, we have Whangarei Harbour up in the far north. This is a much smaller estuary, but it's actually a much deeper estuary than these other three. So although there's some commonalities, there's some important differences in these four harbours that will allow us to test a few of the mechanisms that we think about what might be driving differences in the health of different ecosystems, the accumulation of biodiversity, and those sorts of things that we're all particularly interested in. So the other thing I want to point out is that we're going a little bit rogue here, and that I'm going to be focusing on a number of different harbours as well as Auckland's harbours. So we've started projects in Tauranga Harbour as well as Lyttelton Harbour in and around. Lyttelton Harbour is a harbour that services the city of Christchurch, which is the South Island's largest city. So we've got some collaborations going on there to try and, again, find out if there's some common mechanisms or common problems facing all of the harbours within the New Zealand context. So if we think a little bit more about the working groups within the World Harbour Project, I feel a little bit like I'm preaching to the choir here, but we have the Water and Sediment Group, the Green Engineering Group, multiple users and multiple uses, and the Education Outreach working groups. The two working groups that my research feeds into the most, the work that I'm going to present today, is the Water and Sediment Group and the Green Engineering Group, though there are components of working groups 3 and 4 in the different projects that we're doing. We'll start off by focusing on green engineering and an experiment that should be pretty familiar to everyone here. So it's the large, globally replicated green engineering experiment where we had differences in complexity manipulated as well as the presence or absence of a native bivalve. Much like Hobart, we decided to use a mussel. Ours is a green lip mussel, and we had plates with and without green lip mussels. And here are just two examples that I've pulled up of a flat plate with mussels and a highly complex plate without any mussels. And although this is early days for us, we have finished the experiment. We harvested it about 3 weeks ago. Connor, my master's student, who's actually done the bulk of this work and has done a really, really good job of it, is currently getting his head around multivariate statistics, and we're going to run him through that in the coming months, which should be fun as he writes up his thesis. But just very, very preliminary results at this stage, focusing on one of the blunter measures of biodiversity that we can come up with. Species richness, so the average species richness on the different plates. We've got the 6 different treatment combinations on the right hand side here, seeded and unseeded, flat, medium complexity and high complexity across the first 9 months of the experiment. And I'm going to give away the result a little bit here, in that it suggests that we do have a seeding as well as a complexity effect. And again, these are early results and we still need to confirm all of the statistics behind it, but it's promising at least. So what we can see is that our low flat seeded and unseeded tend to be in the lower half of the plot, with the flat unseeded having the lowest biodiversity throughout. And particularly by the end of the experiment, we start to see a nice sorting where we have the high complexity at the top, the seeded and the unseeded in that order as we go down. So one thing I'd like to point out is that much like the story in Tasmania, we've also found that this little guy, so this is the oyster blenny, has really taken a liking to our high complexity seeded plates. And where we've tended to find it a lot is inside the shells of the dead mussels. So the mussels that we attach to the plates, those that died, they tend to be habited by this blenny. New Zealand doesn't have many blennies, but we are the centre of biodiversity for triple fins, and they've occupied a lot of those niches that blennies would occupy in other parts of the world. And there is evidence that this little blenny is competing with some of the native species for those habitats. So again, a scenario of be careful what you wish for, but still a very interesting result, and it will be really fantastic once all of the data from all of the partner nations starts to come in. How common are these effects where we might be enhancing the numbers of unwanted species relative to wanted species, native species? So that's the wrap up that we have so far of the global green engineering experiment. One thing I'd like to flag is a project we've got coming up, which has really been spearheaded by a colleague, Oliver at the Coughanowr Institute in Nelson, in the north of the South Island. And really what this project is trying to focus on is enhancing the population density of culturally significant species. So this project has a really strong influence from traditional ecological knowledge and how we can incorporate that into our urban design. And I don't know how we did it, but one thing that Ollie managed to convince the Littleton Port Company when they were planning their recovery plan following the Christchurch earthquake is that they had within this recovery plan a commitment to enhancing net gain in mahinga kai. So mahinga kai is Māori for places to gather seafood. And I think, and based on our experiences with the initial phase of the green engineering experiment, those kinds of technologies are immediately applicable to this kind of goal that's been written into the recovery plan for the port itself when it undergoes its both repairs and expansion into the future. And mussels seem to be a species which are focused on a lot in New Zealand. So here in Auckland, in this context, we have here members of the local iwi who have been out placing tons and tons of these mussels on the seafloor, both as bioremediation agents, but also in an effort to try and enhance the local densities of these shellfish that can be then collected for food. So there's some obvious connections there between what they're trying to achieve at Littleton Port and also between the early days of these experiments within the World Harbour Project. And one thing that, another piece of preliminary data that we've been able to pull out from that we've used as part of applications, so we just look at the number of mussel recruits per plate, and this is at the end of the destructive sampling that we've just done, so this is at the 12-month period. We can see that we've got an effect of the seeded plates tended to have greater numbers of mussel recruits. But once we got to those really high complexity plates, the differences between the seeded and unseeded plates weren't very high. So a recommendation that could be made to the Littleton Port Company is if they're going to be building low complexity structures, they might want to consider seeding them with mussels, or from the get-go, they can try and build structures with greater surface complexity. So these are recommendations that are immediately applicable to managers and what they're trying to do based on that report, where they're going to try and enhance mahinga kai. Another project that I'll flag is that, and this is a project that involves Tauranga Harbour as well as Littleton Harbour, is that we're going to try and understand where New Zealand's placed in terms of green engineering and attitudes towards green engineering on a national scale. And we're going to try and provide some preliminary data to complement what we've already got going in Waitemata Harbour in Auckland and these other two locations. These other two very important locations. So Tauranga is one of our largest container ports, and the Port of Littleton is the port that services Christchurch, which is the South Island's largest city. So watch this space. And to do that, we've applied through Ministry of Business, Innovation and Employment to get some money. And these are the key or the lead researchers on the project, but there is quite a strong contingent of Australian researchers from throughout New Zealand that are contributing and hoping that we get funded for this project, because I do believe that it could produce some outcomes which will be immediately applicable at a national scale. So moving on to the Water and Sediment Quality Working Group and the kinds of studies that are going on there. There is already a pretty intensive contaminant mapping program within the Waitemata and Manukau harbours. And just for reference here, the green, orange and red dots in this bottom left plot are green for the ANZAC guidelines that were talked about from Hobart. Those levels in Hobart are absolutely mind-blowing. We are well within that range, but it's been given green, orange or red just relative to what we have going on within our local context. And these projects are headed up by Marcus Cameron at the Auckland Council, who's been working in close collaboration with Working Group 1. So again, I won't want to steal Marcus's thunder. Maybe he can tell you about what they've been finding at a future date, but also more recently Chris Garton from Watercare, which is a subsidiary of the Auckland Council. But what I want to flag is a project that we've just started with Professor Russell Death at Massey University in Palmerston North, looking at integrated catchment management. So one of the things that Russell is very good at is applying these Bayesian belief network models to map and predict the health of waterways around New Zealand. And Russell has been incredibly successful in using these maps to motivate change at both regional levels, but also at our national governmental level in how we manage our freshwater resources. And what we can see here, Russell's generated this map for the Auckland region based on a project that we've got going on in the Kaipara Harbour, where we've got a lot of sort of yellow, sort of moderately affected regions, some quite heavily affected regions in and around Auckland City itself. Fortunately for us, this green region down here is the catchment that feeds the reservoirs for all of the water for Auckland. But we can start to see some red areas that are creeping into the Kaipara Harbour here, which are the focus for this study. So what we're hoping to do with Russell is bring together these two different data sources and see if we can generate base and belief network style analyses that incorporate both what we know about what's going on in the freshwater systems and how it's being deposited in the marine systems, and use that to really try and motivate change at a governmental level, given the success that Russell's had in this space in the past. So we've focused mostly on Working Group 1 and Working Group 2 in this talk, but there are components of multiple users and multiple users, particularly based around the inclusion of traditional ecological knowledge and the goals and aspirations of local iwi, local Indigenous peoples, in trying to engage with green engineering technologies. And we believe here in New Zealand, giving our own cultural context, that's a really good way to try and get public support and social capital for green engineering initiatives. The projects that I have outlined straddle a bunch of different harbours, despite this being, I'm supposed to be presenting on Auckland and the Waitemata Harbour in particular. But I think, much like the World Harbour Project itself, things are most powerful when put into context. In the World Harbour Project, we have the global context, and much like Australia is starting to generate with Hobart and Sydney and different locations like that, we can actually start to give the results that we're finding at a local scale a little bit more of a point of reference. So thank you all for listening, and I was asked to provide a suiting picture so that we can all start the questions, and here is such a suiting picture. Thank you all very much, and thank you, Karen, for organising this, and the rest of the World Harbour Project team. Thank you all.
Thank you, David, and thank you to the panellists too. We only have a very short time for questions, unfortunately, so for those who haven't asked a question, you can either click on the hand and I'll unmute you, or you can type your question in. But we do have a first question from Sydney here, which is Edwina. I think she has a question for Christine or Katrina.
Hi, Christina. What do you think are the key issues in the Derwent Harbour going forward?
I think there's a number of priorities going forward. One is around continued remediation of heavy metal contamination, and there's some really excellent work going on at the zinc smelter at Nearstar. They have a big groundwater remediation program there, which is the main remaining source is heavy metals in groundwater, and they're actually pulling over 100 tons of zinc and other metals out of their groundwater every year, and they've probably got another 50 tons to go. So that's been quite successful. Another key part of it, though, is managing the legacy of heavy metals that we have existing in the sediments, and there's been a lot of work around that in collaboration with IMAS and others. And a lot of that is really around managing nutrients and managing oxygen to try and ensure that the metals are bound to the sediments rather than diffusing, for example, into pore waters. So I don't know if you want to add to that, Katrina?
And I think one of the really interesting things there is it's the complexity of it. So, you know, managing eutrophication and organic inputs is actually implicitly tied to managing the ongoing effects of the metal contamination. And sometimes we try and do some remediation somewhere, but it has the flow-on effect is not what we expect elsewhere. And we've seen that with some of the pulp mill remediation and things, that doing the best you can to fix one problem is actually enhancing another. So that complexity of interaction, I think, is really important. So one of the key ones is the catchment stuff. So there's major development going on in the catchment, and you know, really good that that's happening in one context, but they have to be able to understand the flow and effects to the full water body. And I don't know that we've always really captured that well, and I think we're starting to see the effects of it. So it is, I suppose we're calling integrated catchment management, multiple use management, whole of system management, and maybe our boundaries need to go wider than we had before. Does that answer your question?
Yeah, thanks. Seems like a common problem.
Yes.
I know David had a question. Sorry. David, I know you had a question, so if you can just put that through very quickly and get some very quick answers, then we have to finish up, I'm afraid.
Cool. I guess this is a question for the panel members and anyone listening. As I sort of mentioned, within the New Zealand context, getting involvement from local indigenous groups, so the iwi, the Māori people here in New Zealand, is an important part of the landscape in terms of anything we want to do, particularly in a marine environment. Are there any other projects going on within the World Harbour Project partner nations that have taken that sort of approach of trying to incorporate traditional ecological knowledge and iwi as partners within the more rigorous, rigid scientific framework?
We have, Katrina here, we have a couple of projects that are looking at that much more for a resource use and resource management perspective than from a whole of system management perspective. So I was really impressed at some of the stuff you were talking about, David, in New Zealand. I think where you're going is absolutely the right way, so it'd be really lovely to expand it into that. But I think at the moment the key focus, as I'm aware, and I might be wrong, is much more in the how do we do the resource management, and whilst that might include catchment and environment, it's not explicitly starting from that base.
I see. Cool. Thank you.
Just a quick question from Judy in the States, if we finish with that one as well. Judy's asking that many Australian estuaries are using report cards to track status and trends. Are any of the panel members considering initiating report cards?
We do report
I can just jump in.
Sorry, go ahead.
Where you go, Katrina?
Okay, it's Christine here. We do a report card every year for the Derwent, which really looks at three main things. One is cumulative loads from point and non-point sources. We also track water quality conditions and trends and sediment quality, seafood safety. And the other important part of it is tracking actions taken to improve the situation. So that's been quite a popular. We don't give grades per se, but we do track activities and conditions and trends.
I guess within the New Zealand context, rather than a formal report card, we have the traffic light system that I showed a little bit of in my presentation, where different regions are given different coloured circles, and people in the surrounding regions, or the people that are most likely to use those resources, are made aware of the grade for those areas.
All right.
Yeah, I guess from a Sydney Harbour perspective, it's always been something that particularly the Sydney Harbour Research Program has been interested in working towards. I think part of our problem is developing that integrated enough program in which we can then start having these large report cards. I mean, certainly the local councils that govern different areas around Sydney Harbour are very interested in those sorts of things. But it's just getting a big enough integrated program that it makes sense, I think, from our perspective.
All right, well, I think on that note we should probably end a little over time, but thank you everyone for attending. If anyone has more specific questions for our panelists, their details are on the World Harbour Project website under the Partners page, and we'll shortly be sending out some more information on our next webinar, which at this stage is scheduled for the 27th of April. So look forward to seeing everyone there. Thanks for your time.
Thank you.
Thank you.
Bye.